In this problem, we're again composing a trig and an inverse trig function, but now instead of having a number here, I've got a variable here. Now, I do tell you that that variable is representing something positive. And I will promise that if I am asking you to do something like this, where you're composing trig and inverse trig, evaluated at a variable, I will give you some information about that sign. If I didn't have this information, I'd have to do this by breaking it up into cases. Because I'd have to say case 1, what if x is positive? Case 2, what if x is negative? Now it turns out for this particular problem, I'm going to get the same answer either way. But I don't want to assume that, and we will see a case in which we don't get the same answer either way. So I will always give you that information, but just be aware, because you might encounter this in calculus. If you're just doing this, there would be two cases, x positive and x negative. Technically, there's a third case, what if x is 0, but that's a very, very specific case, and you can usually just check by inspection that the formula that you get in the other two cases works in that case as well. All right, so I'm trying to evaluate this. I'm going to call this theta. And so we're basically trying to evaluate cosine of theta. So since I've used up my board space here, I'm going to put my blanks here. Two-step process, the sine and then the absolute value. What this tells me is that sine of theta is equal to x, and x is in the interval from negative pi over 2 to positive pi over 2. Okay, now that interval corresponds to quadrants 1 and 4. Okay, I need to know the plus or minus sign of things in order to know what quadrant I'm in. Notice if I just knew this was x, I wouldn't know whether it was positive or negative. But in this case, I was told x is positive, so we're in quadrant 1. And if we're in quadrant 1, cosine will be positive as well. Fabulous. Okay, and so if we're in quadrant 1, our angle theta is its own reference angle, essentially. And sine is x. Now I'm just going to write that as a fraction, because I like to think of my outputs of trig functions as trig ratios. Sine is opposite over hypotenuse. And x is a perfectly legitimate side length here, because it's a positive number. Okay. So the absolute value that I'm going to put here is going to be cosine of theta, which will be adjacent over hypotenuse. So I need to solve for the adjacent side. That's Pythagoras. 1 squared plus a squared equals x squared. A squared is x squared minus 1. A is a side length, so it's positive, the square root of x squared minus 1. Excellent. So now I can say cosine is adjacent over hypotenuse. So that's going to be the square root of x squared minus 1 over 1. And of course, I don't need to write that over 1, and I don't need to write that plus sign. So my answer is just root x squared minus 1. Excellent. I want to do another example, but where x is negative, because there I want to be very clear about what my expectations are for showing your work. So let's try this. Let's try tangent of arcsine of x over root x squared plus 9, where x is less than 0. Okay. So notice it's not just x here. It's this expression that has x's in it. Okay. But this time I'm told that x is a negative number. Okay. So I'm going to call that theta. And so we're basically evaluating tangent of theta, which is going to be a two-step process, taking into account the sine and then the absolute value. Okay. So what I know about theta is that sine of theta is x over root x squared plus 9, and theta is in the interval from negative pi over 2 to positive pi over 2, because that's the range of arcsine. Okay, fabulous. Now that corresponds to quadrants 1 and 4. So is this a positive or a negative number? Well, we're told that x is negative. Okay. So if x is negative, the top is negative, but the bottom is going to be positive because it's a square root, and the principal square root of anything is either 0 or positive, and it can't possibly be 0 because what's under the radical is 9 or more. Okay. So this fraction is a negative over a positive. It's negative. We're in quadrant 4. I need to see that you're taking that into account. Now, I don't care if you do things exactly the way I do or not, but I do care that you justify all of your steps. So you've got to take into account the fact that x is negative, and that puts you in quadrant 4. So now if I go to draw my theta, I can say that's going to be in quadrant 4. So theta is essentially a negative acute angle. I like to work with my reference angle, so I'm going to go ahead and call that alpha and label that as alpha. What I know about alpha is that sine of alpha would be the absolute value of x over root x squared plus 9, which is the absolute value of x over, since this was already positive, I don't need the absolute value on the bottom. But I do need it on the top. Okay, it's not correct to say that this represents sine of alpha because this is a negative number. Alpha is my reference angle. It's an acute angle. It has a positive value for its sine. So I'm going to go ahead and label my triangle, labeling it with the sides for alpha. Okay. So if this was sine, I can do this as opposite over hypotenuse. So I can say that this is the absolute value of x, and this is root x squared plus 9. Okay. And then I can solve for this. Now, if I was labeling my triangle with signed sides, I can see that in this case, this ought to be the negative side because my capital Y value here would be negative. And x, without the absolute value, does represent that. Okay? But I want to be careful because if I'd had the x in the denominator, which corresponds to the hypotenuse is never negative. Okay? So I can't just blindly assign x. So my habit is that I always label things with positive side lengths for the reference angle, and if x is negative, I just put the absolute value of x in there. Okay. If you wanted to do signed sides, you could, but I do need to see that you're working in quadrant 4, and I would suggest if you're doing signed sides, and you call that x, that you just write a little reminder note to yourself, hey, that represents a negative number. Okay. All right, let's solve for this side, which would be my adjacent side. So a squared plus the absolute value of x squared is equal to, this squared will just be x squared plus 9. Now notice, when I square the absolute value of x squared, it just becomes x squared. And now I can subtract x squared from both sides, so a squared is 9. A would be positive 3. Okay. It's positive if I'm labeling side lengths. It would be positive even if I were labeling signed side lengths. Okay. All right, excellent. So let's see. We're in quadrant 4, so tangent will be negative. I usually write that right when I figure out the quadrant. I forgot to do that this time. That's okay. This sign being negative put me in quadrant 4, which gave me that sign. Now what I'm going to do is I'm going to attach tangent of alpha. Tangent is opposite over adjacent. So this would be the absolute value of x over 3. But I can simplify things further. I used the absolute value because I was labeling side lengths and I wanted to have something positive. But with the absolute value function, I can write that as a piecewise function because there are really two rules. One thing I do if x isn't negative and something else that I do if x is negative. The absolute value of x would just be x if x is bigger than or equal to 0, but it's the opposite of x if x is less than 0. That does not mean negative x, that means the opposite of x, and I only use that rule if x is a negative number. The opposite of a negative number is negative. Okay, so I can say since x was negative, I know that that's the opposite of x. So I've got negative, the opposite of x over 3. Those two negatives will cancel, and that leaves me with x over 3. Now you might say, why did we bother with that absolute value in the first place? If we just labeled it as the sine side being x, we'd be great. It would work out in this case if we labeled things with sine sides, because that side happens to be the one that is negative. But there will be times when x is a negative number, but it's representing its position in the trig ratio would put it as one of the sides of the triangle that's positive. So I don't want to assume that things are going to work out nicely. I always play it safe and say I'm going to label side lengths as positive numbers, and I'll just deal with the absolute value. Okay, excellent. What we're going to do now is we're going to move on and define the other three inverse trig functions. I realize I haven't given you one of these to practice on. I'm going to give you a chance to do that once we've defined the other three inverse trig functions.